Afternoon. Thank you once again for joining us this afternoon. This session is a GCSE Maths session, and we're going to be focusing on solving equations using graphs. It's going to be delivered by the amazing Molly. Molly, as a lot of you already know, is currently studying computer science and mathematics at the University of Bath. She's delivered many sessions here at my tutor, and you're definitely going to be in safe hands today. For new joiners, just to note that you can put any questions you have within the chat or the Q&A functions. Both of them are located at the bottom of your screen. All right then, Molly, I'll pass it over to you if you're ready.
Cool. Yeah, I'm ready to go. Hi, everybody. Long time no see, right? So if you were at the previous one that literally just finished at 3, wow, double maths on a Friday afternoon. Who allowed it? Disgusting, right? But hopefully we'll make it kind of fun, if that's possible. As was said, you can whack messages in the chat as we go along. I'm normally, touch wood, pretty good at staying on top of them, especially if it's stuff like, Molly, slow down, Molly, speed up, Molly, you make no sense, Molly, stop trying to be funny, etc., etc. So let's jump straight into it today. So we're going to be covering, previously in graphs, we've looked at the basics of what they are, so how to find coordinates, what y equals mx plus c means, and then in the last hour, we looked at some really useful, super useful equations about how to calculate gradients and then how to find the equation of a line from just a gradient and a point on that line. We've also talked about parallel, perpendicular. We've covered a lot in just 2 sessions, I think. We've done what I would call most of graphs, everything you need to answer most questions. So today we're going to be going through a couple more specific kind of bits. So to start with, we're going to be talking about solving simultaneous equations on a graph. So I think I'm anticipating that this will be most of the lesson. So this is, we have covered simultaneous equations, I think, have we? Maybe we haven't, maybe I'm getting confused. But simultaneous equations are when you have 2 equations in 2 unknowns. And we're going to look at how we solve those using a graph. We're also going to look at how we estimate solutions when one of them is a quadratic. So, ooh, scary, right? So, someone says we have, good. There's been a lot of these. Cool. And then the second thing that we'll cover, which will take up the rest, how much the last third or whatever, will be some distance time graphs. So this is where we've got, Sally walked at a pace of this and blah, 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 and either plotting them onto a graph or most likely interpreting graphs. So this is quite important actually, because it's about, a lot of maths is just purely theoretical and looking at triangles and you think, well, when would you use that? But this, I think, I don't know, applies to the real world a little bit more. So I'll stop waffling on and we'll jump straight into solving simultaneous equations. So I'm going to start with this one. Ones where they are already drawn on. So the question here, let me pop on the graph, it says, using this graph, solve the simultaneous equations. And then we have these, y equals x minus 1 and 3y plus 2x equals 12. So I think maybe this sounds a bit weird to look at first, and maybe it's obvious to you, or maybe you've seen this before. But I don't know how you can kind of use that using a graph. But, well, first of all, the thing to notice is that these are the lines that have been plotted. That's exactly what those are. And if we think about what simultaneous equations are, well, what it means is that for the values of x and y that are the solutions, this equation holds. So essentially y is always 1 less than x. That's what this one really means. We can actually really think about this one. And here, I mean, we can't really interpret this very well. I can't anyway, but 3y plus 2x equals 12. And what this means when we plotted them is that at every single point along here, y is equal to x minus 1. let's think about it. Let's take this point. Y is 5 and X is 6. So Y is X minus 1. 5 is 6 minus 1. And that's true at every single point, even here, where you have maybe 3.77. And then here we'd have 4.77. So it's true at every point, this equation. And then we look at this equation, 3y plus 2x equals 12. That's this line. So at every single point, let's pick one. Let's pick here. 3y, well, y is 0, so that's nothing, plus 2x, 2 lots of 6, is 12. Perfect. That really works. So if this equation is true at every point along here, and this equation is true at every point along here, when are both equations true? Well, that'll be where they meet. Because at this point, right here, let me put a little marker on it. That point, that little pink dot, that point lies on both of the lines. So both of these equations are true. Hopefully that makes sense. Just shout if that doesn't make any sense. So this is a really cool thing. And then we can look at, well, where is this point? This point is at 3, 2. So they meet, they intersect at the point 3, 2. And what that means is x equals 3, y equals 2. And there are your solutions to the simultaneous equation. Someone said they don't know how both equations are true. Maybe I worded that weirdly. So that's just kind of the definition of simultaneous equations. So if we were trying to solve this equation, we'd say this equation is true. Basically, if you plug x and y into this equation, it will work. And if you plug x and y, the same x and y into this equation, it will also work. So that's what we need, an x and a y that we can plug in. Oh, it would work in this equation, but it wouldn't work in this one because it doesn't lie on this line. Oh, someone said, can I slow down in explaining it? Yes, I'm a very hyperactive person, so I tend to talk fast, so please do let me know. How about I do it with another example, and I'll see if I can go a little bit slower. So, this one, we've got to do a couple of things. So they've already drawn one line for us. Let's just think about this one line for now to think about what on earth I was going on about with things being true. So we've got drawn for us the line y plus 2x equals 5. That's what this line is. Now, that means that at every single point along this line, if we take the value of y and twice the value of x, it's going to be 5. So let's think about that. Let's think about this point here. I'll draw on it and just erase it a bit. So this point. The value of x is 1, and the value of y is 3. Well, if you take the value of it looks like I've written 0. I was circling the 1, but the value of x is 1, and the value of y is 3. If we take the value of y, 3, and twice the value of x, so twice 1, which is 2, those do indeed add up to make 5. And we know that that's true because it's on this line. That's exactly what this line means, is that every point along it, this happens. That's just what drawing that line means. Hopefully that makes sense. If we pick a point away from this line, that can't be true, because this line is exactly what that means. This line is the collection of points where this is true. So let's think of, why don't we think of something that satisfies this and see that it's on here? So what if y was 4? Then x would have to be a half, right? So we take 4 and we add 2 lots of a half and we get 5. So let's find it. 4, half. There it is. It's on the line. And of course it is, because that's what this line means. So hopefully that makes a bit more sense, just thinking about it in terms of one line. Yeah, what the actual drawing of that line has meant, I suppose. Yeah, every point along here, this is true. Now, this looks a bit unrelated, but I promise it won't be. We're going to make this table of values. Now, wherever you see a table of values, you're probably about to draw a line. So let's fill it in and I'll show you how on earth we use these. So I'll fill it in blue so that we can distinguish it. So it's for y equals 2x minus 1. Now this is kind of like what I was doing above. We think of an x and we see what the y would be to get out. So when x, for example, let's look at one that they've already done. When x is 0, it means we plug 0 in here, y is minus 1. When x is 2, y is 2 times 2, so that's 4 minus 1 is 3. So we're just going to do exactly what they've been doing. So when x is minus 1, y is minus 2, because it's 2 times minus 1, minus 2 minus 1. That's minus 3. When x is 1, we get 2 minus 1, so it's 1. And somebody said here, is it adding 2? Yes, exactly right. And that's actually because here, if we think about this in the form y equals mx plus c, this is the gradient. So whenever we increase x by 1, we're increasing y by 2. That's exactly what a gradient of 2 means, so well spotted. And then finally, if we put in x is 4, we get 7. 8 minus 1 is 7. Now this is really, really useful because the next, I haven't written, put it on here, but the next part of the question is going to be draw this line. So draw y equals 2x minus 1. So let's do that. So what we do is we just plot. What we've got now is actually a lot of pairs of points. So we've got minus 1, 3. So minus 1, 3. 0, minus 1. Please let me know if you don't. Oh my gosh, I've done it. Minus 1, minus 3. Sorry, everyone. 0, minus 1. 1, 1. 2, 3. 3, 5. 4, 7. That was quite bad. Does anybody not understand where that's coming from? I hope everybody understands that. Don't worry if you don't, though, just shout and I'll explain it again. And now, basically what we've done is we've found a load of points that we know lie on this line. So now we're going to join them up. Because if they all lie on the line, they all have to be on the line. So the line must go through them all. So I'm going to cheat and use the line drawing thing from my tutor. Lovely. So that'll do, right? This is the line that we've just drawn. This is the line of y equals 2x minus 1. That was some horrible writing. Don't know what happened to my pen there, but oh, someone's just said about struggling to read graphs. How do you know how much each unit goes up by? That's a really good question. So here, this one's really interesting because the scale is actually different on each axis. So here we can see that one big box is 1, whereas here one big box is 2. So you've got to look at the numbers that you have given and then think about, so for example, let's think about how I plotted this point, 2, 3. So it's along the corridor up the stairs. You might have heard that before. So if you've got the point 2, 3, basically all this is the intersection of where the x value is 2 and the y value is 3. That's what a point actually means. So we have a look here. So we go across to 2 because x is 2. And then so we know it's got to be somewhere along this line. And it's where y is equal to 3. And the way that I know that is because if this is 2 and this is 4, 3 has to be exactly in the middle. And this is made up of 10 mini squares, so I know that it's 5 squares up. Hopefully that makes sense. Yeah, someone's already got the point of intersection, which is fantastic. So yeah, the next question, which again I didn't paste on, but it is the next question, it will be, what is the solution to the simultaneous equations y plus 2x equals 5 and y equals 2x minus 1. So I guess kind of predictable, if you've been made to draw two lines that it quite clearly intersect, then it's probably going to be solving them. And I'll explain this again, hopefully a little bit more slowly and clearly. This actual question means where is this true and this true? So what values of x and y can I pick? so that when I take y and I add it to twice x, I get 5. And when I take y, it's the same as twice x minus 1. What are the values where both of those are true? Well, we know that this line, all of the values that is true for is along here. That's what I was saying at the beginning about that's what the line is. This is the collection of points where this is true. So maybe y could be 5 and x is 0, but then that doesn't work for this one. So that's what I mean. You've got to find that sweet spot where it's true for both of them. Well, where is there a point that's along this line and along this line? So true for this and true for this. It's here where they intersect. So let's zoom into that. And we can see, because we've drawn it so beautifully, we can see that it's here. And this is 1.5 or 3/2, however you want to say it, 2. So the solution, we can either write the solution in a couple of ways, either as the coordinate, 1.52, or we can write x equals 1.5 and y equals 2. Both of they're equivalent ways of writing the same thing. Yeah, brilliant. So I think people were getting that. Someone said, what year group will we learn this? That's a very good question that I don't know the exact answer to. Year 9 or 10 would be my guess. Maybe I'm wrong though. I genuinely can't remember. Good to learn at any point though. Someone said, so to solve a simultaneous equation, we need one numerical character to make it solvable. Good question. Yes, because you need to know, I don't want to overcomplicate it. Basically, yes, you do. Yeah, because you need two different relationships. You couldn't say, yeah, you need at least one, because you couldn't say y equals x and 2y equals 2x, because they're the same equation. One of them's just double the other. So you do need two distinct equations. And to do that, you have to introduce adding or subtracting a number. And someone helpfully said that it's year 9, apparently. Can you learn this around then? Cool. Let's have a go at another one, seeing as we're having so much fun. I'll do this one, I think. I'll get this. So this is one where I haven't done one where you have to draw anything for this one. This is just a reading off the graph kind of thing. So this diagram shows the graphs of y equals half x plus 2 and 2y plus 3x equals 12. Horrible kind of sounding equations. And then we want to use the diagram to solve those simultaneous equations. Yep, these are what have been drawn, so we want to solve these. So again, I'll kind of re-explain it just one more time before we move on to anything new. This equation is true along this line. This equation is true along this line. Solving the simultaneous equations means finding where they're both true. So where is there a point that's along this line and also along this line? Here. That was quite a bad point, wasn't it? Not there. Here. And we can see where that is. That's at 2, 3. So again, we can either write the answer in the coordinate form or x equals 2, y equals 3, which I know a few of you got before I'd even gone through it, so well done. Now, someone's just asked a question which leads me beautifully into the next part. So someone said, will it always be a straight line? No. So the only way that you can tell for sure is by doing this algebraically, which we've covered before. Straight lines give you a really, really good chance that you're right, because we can draw straight lines with a ruler. We know exactly what they look like, and we can connect up points very accurately if we've got good axes. However, what if we have one linear equation like one of these and then one quadratic? Let's have a look. So I think it's in here, yeah. So we want to use the graph to solve these got to be careful of the word solve. It will actually be approximate or work out an approximation. And the reason is because when we draw this quadratic, only a computer could get it exactly like a curve. There's no way of drawing a perfect circle, a perfect curve. Yeah, exactly. Someone said you can't draw quadratic curves with a ruler because it has to be a smooth curve. And that's exactly right. If it's not a smooth curve, you won't be hitting all of the points for which it's true. So it's really important that it's a nice smooth curve, but no human is going to be able to draw it like that. You'd need a robot or a computer. For linear graphs, they do have to be straight. That's the definition of a linear graph. Exactly. Yes, someone said, oh, you need Desmos, which is exactly what I'm going to use. Just in case you haven't been to the previous sessions, I keep ranting about Desmos. They should sponsor me. Gosh, it's a graphing website that's fantastic, and I will show you after so we'll approximate them and then actually find it on Desmos. So let's have a look. Let's draw the straight line first, because that feels a bit nicer to do, right? And actually, we don't even really need to draw up a table for this. You only really need 2 points to plot a line. Because if you think about 2 random points, there's only 1 line that goes through both of them. We're going to always do at least 3. For curves, we're actually going to do like 8 or something. But for lines, we only need 3. Because you only need 2 and then the third just confirms. If they're all then in the same line, you know you haven't made a silly mistake. So let's just think about this line to start with. So x plus y equals 8. Like I said, I'm not even going to draw a table. I'm just going to think at what points is x plus y equal to 8? Well, 0 and 8. What about 1 and 7? Gosh, this is very hard to do. 1 and 7. 2 and 5. 3 and 4. 4 and 3. We could do some negative ones as well, but that's all we need. We can see that those are in a straight line there. Oh gosh, are they? I don't think they are. Oh gosh, no, I did those first 2 wrong. See, this is why it's quite difficult with these graphs. So we want 0 and 8, so we count 5, 6, 7, 8. And check that that works, because then that's 9, 10. And 8, 1 and 7, 2 and 6, 3 and 5. Oh yeah, it's going up to 8. Sorry, that's my fault. I started adding them up to 7 at one point for some reason. 4 and 4. Now we can see that these are in a straight line. Hopefully you can see where I got this. I'm just choosing points where the x and the y values add up to 8, basically. And then we'll connect those with a line. And what we're going to do is we're going to connect them, but try to extend a bit further than just the connection. It's going to go badly when I first do it, but then I'm going to adjust the line on here. So there we go. That's, oh gosh, it's really very difficult. Oops. Okay, you know what? I've clicked off it. There we go. That's good enough for me. I know that that's not precise, but that's good enough for me. So that, I'm just going to label it. I think labeling them is really important so that you don't get mixed up. So this is the line x plus y equals 8. And hopefully you can see how I drew that. I just picked some points that I knew were on it. Someone said a really good question. First of all, someone said how many marks are these questions? Ones with quadratics, probably 4. Ones with lines where they're already drawn on, just 1 mark. And ones where you have to draw the lines or do a bit extra, 2 or 3 marks. And someone said, is there a reason why you have to extend the line to show that it continues? Yes, because if we've just connected up the points and then our other one crossed it somewhere over here, we wouldn't be able to see that. So we've got to extend the line as much as we can to make sure that we know where it crosses our other line. Now let's think about our quadratic. And I'm going to do a table for this one because I think it's a bit easier. Y equals x squared plus 2. So the way that we do these is we think about our x values that we have. So based on our graph, it seems sensible to go from -4 to 4. So we do our x column, -4, -3, -2, -1, 0, 1, 2, 3, 4. And then our y values we're going to fill in. So I've just made this little table. And we're going to do what we did before and work out some points where this is definitely true. So some points that definitely lie on the curve. Plot them all in and we'll see our curve happening. So let's think, when x is -4, what's y? Well, it's x squared plus 2. X squared is 16, because -4 squared is still 16, remember, because the minuses cancel out. And add 2 to that, we get 18. X squared plus 2 when it's 3 is 9 plus 2. When it's 2, it's 4 plus 2. When it's 1, it's 1 plus 2. So all I'm doing is I'm squaring this and adding 2, because that's exactly what I'm being told to do. So I'll fill in the rest, and it's actually going to start going back up here, because 1 squared is the same as -1 squared. So it goes back up. Now let's plot those. This could go badly wrong, couldn't it? So we've got, what I'm going to do is take a photo of it so that I can zoom in and still plot the right things. So let's zoom in here to make sure that I plot it. I want to do it as accurately as I can to get a good approximation. So when x is -4, y is 18. So that's going to be here. So can you see that? I found where x is -4 and I've gone up to where y is 18. And then when x is -3, y is 11, so that's there. When x is -2, y is 6. For -1, it's 3. For 0, it's 2. And then we go back up again. So for 1, it's 3. For 2, it's 6. For 3, it's 11. And for 4, it's 18. So hopefully, I mean, you can just about see those blue dots on there. You can see that this is making a lovely curve. So let's let's try to join them up. Now, there's no function for me to do this on here. So as I said, we will do it on Desmos so you can see what they're actually supposed to look like. But the trick is just to do it with confidence. So that's not fantastic. And I probably should have extended this out a bit further as well. But that's very wobbly, but hey, I'm doing it on a computer screen. So here are our, here's our line and our curve. So then we're going to do the same thing. Now, because it's a quadratic, when we did solving quadratic equations, you might remember me saying quadratics always have 2 solutions. Well, 2, 1, or 0 solutions. But we're normally looking for 2 solutions. If it's 1, it will be because this is just touching it. Like that straight line will have been like there. You know what I mean? And if it has no solutions, it will be where this is not touching it. That was so straight. But this clearly has 2 solutions because it's got 2 points where it intersects. So remember, x plus y is 8 all along here. And y is x squared plus 2 all along here. So where are both things true? Here and here. So let's have a look at what those are, or approximate. Well, this looks to me like it's -3, kind of, that's at about 12. Maybe that's more like 11 actually. And we can tell it's more likely to be 11 because that's there. And then this point here, so this looks to me like 2 down here and 6 here. And actually we can check that these are true by putting them in. So -3 plus 11, yes, that is 8. And 2 squared plus 2, yes, that is 6. So these are our points. And we've got them, not by doing trial and error, but by actually plotting them and finding what we think they should be. So the points are 2, 6, and -3, 11. So that means that the solutions to our equation are either we can write them as these points, or we can say x equals 2 and y equals 6, or x equals -3 and y equals 11. Either of those ones, they're both equally valid solutions. Someone said, would there ever be a question where you have to draw a linear on a quadratic graph in the same question? That's this one. So that pink one is a linear graph, because by that I just mean a straight line, and the blue is a quadratic. So let's grab up Desmos and you can see what this looks like in a much nicer way. So let's see, what was our first one? X plus Y equals 8. Or actually, I'll try to make the quadratic blue. Y equals x squared plus 2. Oh no, this one's red. Okay, x plus y equals 8. And y equals x squared plus 2. So here you go, a lot nicer. And they've actually shown us these points here, 2, 6 and minus 3, 11. So you can see this looks a lot nicer than what I did. And you can see very clearly these points at which they cross, and it actually tells you when you hover over on here. So that's why Desmos is so cool, because you can check your work, see things a lot clearer. Someone said, how many marks would this be? 4, I guess, for kind of like getting the points right, plotting them correctly, and working out the answer. 3 or 4. Cool. What time are we on? Right. Finishing at 4:15, so I've got 15 minutes before questions. So I think I'm going to go on to distance time graphs. And then if you want me to go over more of these, just ask a message at the end. So let's go over some distance time graphs. So distance time graph questions are ones like these. You have distance here and you have time here. And what this really means is you can see how far away someone is every kind of minute or 5 minutes. So I'll explain what this means, and I'll try to do this part by part. I can't paste too much onto the thing, that's all. Let's take this. Cool. So here is part of Sian's journey from her house to the shops and back. So this is just part of it. So there are several things about a distance time graph that we need to know. The first one is that the gradient represents the speed. Let's think about why that is. The gradient of something, remember, it's the y value divided by the x value. Now here, what's the y value? It's distance. And what's the x value? It's time. And what's distance divided by time? Speed. So the gradient here is exactly the speed. And that means that we can calculate the speed by calculating the gradient of a distance time graph at a certain point. That also means when it's a flat line, the gradient is 0. So the speed is 0. So a flat line on a distance time graph represents someone being stationary. So this is going to be Sian at the shops. So we can see that the shops are clearly 20 kilometers away because she stops when she reaches 20 kilometers. Now, we can see that she's in the shops here, and then she's going to come back. And a negative gradient represents a distance in the opposite direction. So it doesn't mean she's going slow or anything. It means she's kind of going backwards. So she's gone to the shops, positive gradient, stays there for a while, back home, negative gradient. Hopefully that makes some sense. So let's have a look at what the questions are here, and maybe that will make some more sense. So the first one here, so this is exactly what I said, we can work out the speed. So we want to work out Sian's speed for the first 30 minutes of her journey. So let's mark where that is. 30 minutes, that's this line here. So all we need to do is calculate the gradient here. So we may as well use this triangle, this big one. It's 20 kilometers up there. And along here, that's 30 minutes. So it says give it in kilometers per hour. So we'll write that in terms of hours. So 30 minutes, that's half an hour. So let's just work out the gradient, or you can think of it as working out the speed, distance over time. 20 kilometers divided by half an hour. You can put it into your calculator, or just think about it. If you divide something by half, you times it by 2. So this is 40 kilometers per hour. And we can tell that just from a line on a graph. And I think that's pretty cool. So the gradient of this is 40. when the gradient is 40, when you consider this axis in terms of hours. Yeah, brilliant. Some people got that, so that's really good. Okay, let's see what the next question here is. So this, we've got some more drawing on the graph coming up. So Sean spends 15 minutes at the shops. Well, we can see that, look. 3 of these boxes represents 15 minutes, and she's up here for 3 boxes. So that's her at the shops. And then she travels back at 60 kilometers per hour. And we want to complete the graph. So we've got to think about a couple of things. First of all, she travels back to her house. So how far does she travel? Well, she's gone 20 kilometers to get from her house to the shops. So it's going to take her 20 kilometers to get back. You always assume that it's like the same route, unless stated otherwise. She hasn't taken a shortcut or anything like that. So let's think about the time, because that will tell us everything we need to know. So always with speed, distance, time questions, think about this triangle. You've probably seen this before. Distance over speed times time. And what we do is we cover up the one that we're thinking about. So we're trying to work out the time at the moment, so we cover that up. What have we got left? Distance over speed. So let's do that. Distance, it is, she's going 20 kilometers. Over speed, how fast is she going? 60 kilometers an hour. So it takes 1/3 of an hour. What's 1/3 of an hour? 20 minutes. Now this is brilliant, right? Because she leaves here, so at 45 minutes, and it takes her 20 minutes to get back. So 5, 10, 15, 20. So she gets back 65 minutes after she first left. And she was, a straight line means a constant speed. If it's a curve, it means she's accelerating or decelerating. But because she travels back at a constant speed, we know that it's just a straight line. A straight line from here, 20 kilometers when she leaves, down to, I can't see the end of my thing, down to there. That was pretty good. So hopefully that makes sense. And we can note a couple of things. First of all, it's a negative gradient. That's because she's going back to her house. So it's got to be an opposite gradient to her going to the shops. Secondly, it's a bit steeper than this one. That's good. That means she's going faster. And thirdly, we can see that we've hit everything correctly. We'll see that the gradient of this is 60 and it takes her 15 minutes here. So hopefully that makes sense as to how I did that. Yeah, brilliant. I think people got that. So hopefully that makes sense. Okay, let's have a look at some more. So I'll get this question up again and then put the questions one by one on the right again. Someone said, how do you make it straight on the computer? This has a line function. So that's what I use on my tutor. It's got a little line function that I do. So cool, let's have a look here. Right, Anil cycled from his home to the park. He waited in the park and then he cycled back home. So this makes sense, right? So he cycled, so this time, oh, this says time of day. Sorry, I cut that off. So this means 9 o'clock in the morning, 10 o'clock in the morning. So he cycled. So we left at 9:05. You can see that here. Cycled, he waited there for a bit, and then he came back. We can immediately see a few things. First of all, if we want to, we can work out how long you stayed there. We can work out the speeds of cycling. We can work out, I think this one looks steeper than this, so he probably cycled back quicker, and so on and so on. There's a lot that we can tell just from this graph. Yeah, and people are putting on the chat exactly that. Yeah, perfect. So you know all of the information. Brilliant. Okay, let's get up these questions and see what they are. So these are actually not asking us to calculate anything at the moment. So here we go. What time did Anil leave home? I already said this one at the beginning. So we can see that he left here because 0 kilometers means at home because you're 0 kilometers from your house. So at 9:05, it starts increasing. So that is the time they left, 9:05. What's the distance from Anil's home to the park? Well, we know that he gets to the park here because that's where he's waiting. How far is this? 7 kilometers. And how many minutes did he wait in the park? Well, that's how long was he stationary for here? Yeah, brilliant. People are getting this, which is really, really good. And he stayed there, well, we can see he stayed there 9:35 until 9:45. So that's 10 minutes that he stayed there. If it helps, you can absolutely draw on these graphs. I'd encourage you to do it in pencil, just in case you were to draw it slightly incorrectly. You don't want to kind of mess up the graph, but you can draw like this. Oh gosh, don't do that. Like this. And then you can see where they hit at the bottom. I know, that always helped me. So it's a 10-minute wait. Cool, brilliant, well done. So we've got 5 minutes before I open it up to questions. So let's have a look at this one. So this looks a bit incomplete, right? So it looks like we're going to have to do some question answering and then some drawing on it. So, okay. So a man left home at 12 noon to go for a cycle ride. And this travel graph represents part of the man's journey. So it's not all of it, clearly, because, well, unless he didn't go home. So I always, before I even look at the questions, make sure that I know what's going on. So let's see, he cycles 10 kilometers, waits a little bit, cycles a bit more. These seem to be at the same rate. These seem to have the same gradient. So he seems to be cycling at the same pace here and here. And he gets 20 kilometers away in 2 hours. So we can tell that from here. Let's have a look at what the questions are. Let's look at the first two. So these are the kind of the non-drawing ones. So these are the kind of read information, see what you can find out from here. So at 12:45, he stopped for a rest. For how many minutes did he rest? So this is what we pointed out here. We can see actually, that's another good thing to do is to work out the scales. So we can tell here that each box is 1 kilometer. And we can tell here that each box is 15 minutes because there are 4 boxes in between each hour. So we've got 12:45 is here where he stopped for a rest. He stops until 1. So that's a 15-minute rest. So find his distance from home at 1:30 p.m. This sounds like an interesting one. Let's have a look at this. So what we do, let's find where 1:30 is. It's here, halfway between 1 and 2, and go up to the graph. Cool, we can see where that hits it. And where is he at that time? He's here. So what's that? 15 kilometers. So the answers to both of those are actually 15. Yeah, brilliant. I think people were getting that. So hopefully that makes sense. That's what I mean. I really, really encourage drawing on these graphs, like putting things in there and stuff like that. Someone said a really good question. Does a steeper gradient mean a quicker speed? Yeah, exactly right. Because the gradient is the speed. If the gradient is bigger, i.e. steeper, it's a quicker speed. So well observed. Okay, perfect. Now let's do just before questions. We'll do the last bit. It says here, so the man stopped for another rest at 2 p.m. He rested for 1 hour, then he cycled home at a steady speed. So that means it's a straight line. That's just giving you a little bit of help there, saying, don't worry, it's a straight line. It took him 2 hours to complete the travel graph. So We're going to do it step by step. So he stopped for a rest at 2 p.m. Good, that's where we're up to. And he rested for 1 hour. So it's 2 p.m. So he rested until 3 p.m. So let's see where 3 p.m. is. It's here. I might have to zoom in to draw this one neatly. So 3 p.m. is here, because we can tell that's 1, 2, 3, 4 blocks of 15 minutes away. And he rested, so he wasn't going anywhere. So his distance stayed constant. He stayed 20 kilometers away because he rested. And then he cycled home at a steady speed and it took him 2 hours. Well, if he starts at 3 p.m. and it takes him 2 hours, he must have finished at 5 p.m. And he got home at that point. So he goes from where he was when he started off at 3, back home to 5. And it's a steady speed, so we know we're allowed to draw that as a straight line there. Hopefully that makes sense. I know that's quite a hard one to kind of, prove that on there. Okay, so now I'm going to not introduce too much more new information, but open up some questions. So whack them on the chat or the Q&A, I check both. This can be about either of the things we've covered today. So simultaneous, well, in this hour, so simultaneous equations on a graph. If you want me to go over any like other harder ones like that, quadratics, plotting those or anything, or distance time. So I've seen a question I'm going to start with. Will we ever have to draw a curve of some sort in these graphs? That's a really good question. So I'm going to see if I can find some questions like that you'll need to do. I don't know if there'll be any on here, but yes, so while I'm finding this, think of if you have any questions, feel free to ask me. Oh, I can see a hard one here where they intersect, so I might come back to that one. I'll keep it on this page, and for now I'll find some. So times graphs, hard questions. Let's have a look on here, see if there's anything. Let's just go to speed. Oh, none of these have a curve. Ah, here we go. Look at this. Nice. Okay, now this is quite a higher level paper. So is this GCSE? Yeah, I think so. Yeah. So we're going to go over it. Now this is quite a difficult one. Keep throwing in your questions. Cool. Let's go over this. And then if there are no other questions, I'll go over that other one with the lines that we're intersecting. So here's the first thing. Check the axes. So all the other ones that we've been doing have been distance time. Now we've got velocity time. Now, velocity is a fancy word for speed in some aspects. It's speed with an associated distance. If you don't understand what that means, don't worry. It basically means that I can't have a negative speed, right? But I can have a negative velocity. So if I'm going at the velocity of 3 miles an hour, it means that I'm going 3 miles an hour this way. Then if I go at the velocity of minus 3 miles per hour, it means I'm going 3 miles an hour this way. That's all it is. It's speed with a distance, basically. Speed that you can have negative. Yeah, you'll probably have done it someone said we learned it in a physics lesson. This is more of like the mechanics paper type thing, I guess. So yeah, you've got to be really careful. And then you've got to think about, well, what does this mean that our gradients are? That's one thing. Look at the axes and then think about what the gradients are going to be. So remember in our distance time graph, the gradient was speed because that's what distance divided by speed is. Well, now we've got speed divided by time. And if you know, you can think about it in terms of units. That's probably how I would. So meters per second divided by seconds, that's meters per second squared. So that's acceleration. Or just if you know your equations, acceleration is speed divided by time. Or velocity, well, acceleration is definitely velocity divided by time. because acceleration has a direction as well. So we know that the gradient of this is going to be the acceleration. So this is said, work out an estimate for the acceleration of the parachute at t = 6. So that means, what's the acceleration when like 6 seconds after the parachutist jumps out of the plane? So t seconds is here. So let's just zoom in a little bit. So we want the acceleration at this point, where I've drawn that little blue dot. Now, how on earth do you find the gradient of a curve? That seems like quite an impossible thing to do. And in short, it kind of is an impossible thing to do. So we're just going to approximate it. And that's why the question is work out an estimate, because there's no way that we can work this out exactly. So we're going to draw a tangent to this point. Now what this means is we just draw a straight line that just about touches this point. And that's going to be what we then use to estimate the gradient. Before we do that, let's just think about what this means, right? If you've got this curve and the gradient is the acceleration, I mean, we can see first of all that as time goes on, it's getting faster and faster, but at a decreasing rate. Because, you know, it's jumping up faster, faster, faster. Ooh, faster, but a bit slower, if that makes sense. And then if we think about the gradient, this acceleration, it starts quite steep and then it gets flatter and flatter and flatter. So that means that our acceleration is decreasing. So to start with, it's accelerating loads and loads and loads, and it can't accelerate much more because it's already going pretty much as fast as it can. Yeah, so someone said in physics, the tutor said to use a tangent. Perfect. Yeah, tutor's agreeing. So we do a tangent to this curve. So let's see if I can draw one on here. How well will this go? So I can always readjust it if I need to, and I definitely will. I move that whole thing, yes. I just bring this down a little bit here. So I think that's pretty much as good as I'm going to get it. So what it does is it just touches the curve at this point. Just come down a bit further. That doesn't it at this point. I'm too much of a perfectionist. Let's leave it like that. And then what we basically do is say, well, this tiny bit of the curve is basically like that line. It will have the same gradient. So let's see what or someone says, why do you draw a tangent? You've basically got to imagine a curve as an infinite link of little lines. So instead of a smooth curve, imagine it as little lines going like this. So then if we zoom in and zoom in and zoom in, we find this little line. Drawing a tangent is like saying, what's the gradient of that little line? We're just extending it. Hopefully that makes sense. If it doesn't make too much sense, just maybe accept it for now. Just believe me that this is what you do, and then have a look back, have a play around with some other ones, and I think it should make sense the more you do it. So then we want to find the gradient of this. So we're going to find, make a little triangle on it and do that. So let's go from here. This looks like a point where there's something to, let's say here. So I'm using this point and this point. So what's this point here? It's goes down, down, down to here. That looks to me like 4.4, because this middle one is 5. So these go up in 0.2. So that's 4.4. And over here it's 40. And then this one here, over here, it's 50. Now this has got a slightly different scale. So this goes up in 1, so 51, 54. Again, this is only an estimate, so don't worry about being too precise. And down here goes down to 8. So let's think about what the gradient of that is. Well, what's the change in y? It's this bit here. So that's 14. What's the change in x? It's this bit here. So 4.4 to 8, that's 3.6. So what's 14 divided by 3.6? Your guess is as good as mine. But let's round that to 3.89. 3.89 meters per second squared. That's the unit for acceleration. That is a really difficult question, that one. Yeah, exactly. Someone said, so if we zoom in on a circle, is it actually an infinity gone? Yeah, that's a good way of thinking about it. Yeah, exactly. So you've got kind of a pentagon, it's like a 5 gone, it's got 5. And if you keep going and keep going and keep going until you get to infinity, that's a circle. Circle's just an infinitely sided polygon. And that's why we draw the tangent, because we're trying to draw one of those sides. Mind blowing, yeah. Awesome. Okay, so we've got 5 minutes left. So there were definitely some questions that I saw. So someone said, is this the last webinar on graphs? No, there are some more next week on transformations and then a summary. Oh, someone said, do you not differentiate to find the gradient of a curve? Yes, that's only if we, so that's a, I think, is that a further maths term? I can't remember when exactly you learn differentiation, but that's basically a way of exactly finding out this rather than a tangent. But you can only do that if you know the equation of the curve. And here we don't, we just have it drawn. So we actually have to use the tangent rule. See if there's anything else. Nothing else in there. Nothing on the chat. Someone said, will you ever have to find simultaneous equations on cubic as well as linear quadratic graphs? I don't think so, because cubics you need a lot more points to be able to sketch it, because it goes kind of up and then down and then up again. So it's really difficult. So I don't think you'd ever have to do a cubic, so don't worry. You might have to do 2 quadratics. That's not too bad. Again, they just meet in the 2 places. So hopefully that makes sense. Or 1 place if they only meet like this. Yeah, right, I've got 3 minutes. So let's just take a look at this, but not answer it, I think is probably the best way to do it. Well, we will kind of discuss what the answer is, but no point in starting a new question, I don't think. So, okay. Robert left school at 3:30 p.m, so that's here. He walked home, and on the way home, he stopped to talk to a friend, so that'll be here. And his sister Sarah, left the same school at 3:45 p.m, so she left here. And she cycled home on the same route. So here they are. So this is Robert, he left a lot earlier, walked, met a friend, finished walking. Sarah left a lot later, but just cycled all the way back. So I think the most interesting one here, so find the distance he walked. We can find that here, 1.5. We can find the total time that he stopped to talk to his friend here, 5 minutes. Now this is interesting. Write down the distance that Robert had walked when Sarah cycled past him. So that's going to be where they intersect. Look how it links to simultaneous equations. So at this point here, basically when she cycles past him, that means that they're both at the same distance from the school at the same time. That's what it means to cycle past someone, you're in the same place at the same time. So that means that it's got to be there in the same point. So it's here. So how far had he walked? We can look across and read from here, 2 kilometers. So once he's 2 kilometers of the way home, his sister zips past him. So I think that's, yeah, quite an interesting one there. I've got 2 minutes left, so I'm going to say one more thing, just kind of throwing some information at you in the last bit. Or someone's just said, what does the triangle look like for distance, speed, time? Again, I'll draw this for you because it's really important. Here we go. Distance over speed times time. So you cover up the one that you're not using, and the other 2 will give you an equation. So distance is speed times time. Speed is distance over time, and time is distance over speed. And I still refer to this now when I'm tutoring, when I'm doing questions. It's a super useful triangle. So the only thing that I was going to say was that if you ever have something like this, like a speed or a velocity time graph, the other thing that we can actually think about is the area underneath the curve. So that actually comes back to this. The area underneath the curve, so say we have one here that's like this axis here is speed, this axis here is time, and increase the speed, constant speed for a little bit and then go back. What the area underneath tells you well, we calculate the area by doing a multiplication, so speed times time. So the area underneath the curve, so the area underneath a speed time curve tells you the total distance covered in that time. So I don't have time to explain that now, but maybe go look up some YouTube videos on it, find some practice questions. It's not too difficult at all, but I just thought it would be really cool to give you that bit of information to finish on, just in case you hadn't heard it before. And look at that, I finished on time.
Amazing. Thank you for such a wonderful session, Molly. Thank you all for joining us. Remember, all of our sessions are recorded and will be uploaded onto our YouTube channel, so you can go back and rewatch any bits that you need to. Have a lovely weekend all. Goodbye from us.
Bye guys.
Bye.